fundamental theorem of algebra, I feel like this should be like life-changing fundamental theorem of algebra, but to me it's just like makes sense with everything that we've been doing. And it just says a polynomial function of degree n has n complex zeros. Like that's what the fundamental theorem of algebra says. We said before that it could have at most n zeros. Well, now that we can talk about complex zeros, we can say that a polynomial of degree n has exactly n zeros. Some are real, some could be non-real, and a repeated zero, right? Like if it has a multiplicity of 3, that actually counts as 3 zeros. And you have to keep that in mind when you're thinking about finding all your zeros when you do that. So that's something you did in Algebra 2. This is precalculus. We didn't really talk about this in Algebra 2, talking about linear factorization, but it just says that you can write your factors out as a linear factorization, and if it's degree n, then you will have it precisely in linear factors. Some of these linear factors can look really, really ugly because they're irrational or they might be complex, but you can take a polynomial and write it out as a product of linear factors. So some of these could look really nice here, right? And so this is an example that they give using C, where C is a complex number. Like you could write out a polynomial as like x plus 2 times x minus 3 times x plus 7. Right? That would be a really nice polynomial that has zeros at -2, +3, and -7. But what if you had a zero at like 7 plus or minus the square root of 3? That's actually 2 zeros. You could write that as a linear factor too. All you do is you just subtract it over. What if you had a factor, a zero of 2i? Then you would just say its linear factor is x minus 2i. So just know that any zero, you can make it a factor by just subtracting it back over and writing it as x minus whatever that is. So we'll do some of these today. They do get kind of ugly sometimes. They're not going to be all nice integer numbers as we go through here. All right? Conjugate pairs, we just talked about the imaginary zero. I didn't make you write anything here. But if you have one imaginary zero, its conjugate also has to be a zero. Otherwise, you would have i's in your problem, right? So it just says if f of x is a polynomial function that has real coefficients, if a plus bi is a zero, then its conjugate also has to be a zero. That's the only way the i's will go away is if you multiply by the conjugate. So look at number 1 here. It looks very familiar. The last question on chapter 2 tests, I said find a polynomial with the given zeros. The difference is now I can give you an imaginary number as well. So find a polynomial with the given zeros, -2, 3, and 2i. You have to know this about conjugates, about complex numbers, or you're going to get this wrong. If 2i is a zero, what else has to be a zero? -2i. She mouthed it. Okay, say the words. If you forget that, when you multiply this all out, there will be i's in your answer, right? Think about every polynomial function you've ever seen. It has real coefficients. There should be no i's in it. So that's step 1. Know that. And now you just get to do a whole bunch of multiplying, right? So if I'm going to find my polynomial, if -2 is a zero, the factor would be x plus 2. This is that whole linear factorization theorem. If 3 is a zero, that would be x minus 3. And for 2i and -2i, I can just say x minus 2i and x plus 2i. If the direction said write a linear factorization, right, that's a linear factorization. But it says find the polynomial, which means they want you to multiply that out. And here's my advice to you. Multiply your i's out together, right? These are complex conjugates, which means when you FOIL these two out, it should work out really nice. And maybe once we do this, you're going to realize what it works out to every time, and you won't even have to do the work. So for me, when I do this, I'm going to multiply two together, and then I'll go back and I'll multiply it out at the end. And it's easy to make little mistakes, right? Like on the test, you multiply wrong, and you get a negative wrong. Easy to do that, but you want to at least have the process down of what to do. So foiling that out, minus 3 plus 2 would be minus x minus 6. Whole thing about complex conjugates, it's the difference of two squares. So you get x squared. I never put that middle term because I always know it's going to cancel out, right? X times 2I would be 2ix, 2xi, how you want to write that. And then negative 2I times x is negative 2ix. So that middle term will always cross out. And then you're left with, I guess I should, you're left with negative 4I squared. But what do we know that I squared equals? I squared equals negative 1. So negative 1 times negative 4, you get x squared plus 4. Some people are really good at thinking ahead, and they say, well, if plus or minus 2I were my zeros, what would that have to be? And think about that. If you solved x squared plus 4, you'd subtract 4, you'd take the square root, and you'd get plus or minus 2I. So some people are really good at just going straight to that, and it works every time. I tend to just work it all out. So now, just like the one on your test, you just have to multiply it out. Right? So you just want to kind of keep track of all your terms, make sure you don't multiply wrong, which is very easy to do, like I did in class that one day. So I would have x to the 4 plus 4x squared minus x to the 3rd minus 4x minus 6x squared minus 24, I think. I'll make my next one. We have 4 zeros, so it makes sense that we have a degree 4 polynomial here. I always do descending order, not that you have to, right? Like standard form is kind of nice. Some people on the test, when I asked if something was a polynomial, some people told me no because it wasn't in the right order, but you can always switch the order, right? Adding and subtracting, so really, it doesn't matter. I just have been brainwashed to always write the right order. 4 minus 6 is negative 2, minus 4x minus 24. Did you get that? Again, just like the last test, you're probably going to have to do that on the next part of Chapter 2 test, and it will probably have an imaginary number in it just like this, as opposed to what was on the Part 1 test. Complex conjugate theorem. I try to do examples from your homework, like same direction, so you kind of see what it's asking. And this is one direction in your homework tonight. It says, write the polynomial in standard form and identify the zeros and the x-intercepts. What's the difference between zeros and x-intercepts? Or is there a difference between zeros and x-intercepts? I'm just going to take a seat because I feel like you're never going to talk, and I'm just going to wait it out. Maybe you could answer one of them. What is a zero or what is an x-intercept? You figure that out. Say that again? They are the same, she says, aren't they? Anybody disagree with that? They're kind of the same thing, right? Like we say zeros, x-intercepts, what are the other words that mean the same thing? Zeros, x-intercepts, solutions, roots, right? Those all mean like solve the equation. If I asked you to solve this equation, what would you tell me the answers are? It's already factored for you, right? What would the answers be? X equals 3i negative 3i. If I graphed this equation, would those show up as x-intercepts? So they are the same except when they're what kind of zeros? Imaginary, right? So when they're real solutions, right? Real solutions are going to cross the x-axis. Are imaginary solutions going to cross the x-axis? If I graph this equation, those aren't going to cross there. So that's why it says identify the zeros and the x-intercepts. So these we can say are the zeros, the solutions. But we have to say for this problem that there are no x-intercepts. So I feel like I've just committed the thing that I always hate in math, of like in elementary school when you say, what's 2 minus 5, and your teacher says you can't do it. I feel like I've committed that crime by telling you that x-intercepts and solutions and roots and zeros all mean the same thing. Because they do mean the same thing, but if you're talking about what are the x-intercepts, if they're imaginary, they're not. Like, that's like the exception to the rule. So that's kind of just some math vocabulary wording there. What if you work this out? You know what that would be in standard form if you boiled it out? Standard form just means like the ax squared plus bx or whatever, like, and all multiplied out. No, yeah, go. Go.
So if you graph this, how would you graph it for their imaginary?
Yeah, how would you graph it? Well, you'd have to. That's why I want to work it out, because when we work it out, I think you're going to recognize from one of the types of graphs, like what it should look like, right? So if you FOIL this out, multiplied it out, we would get x squared, and then the middle term is going to cross out, and then negative 3i plus 3i, Kinsey says is plus 9, because you'd get minus 9i squared. So what kind of graph is that going to be? It's definitely a quadratic, and what does that plus 9 mean? It's moved up 9. So if you had to graph that and there are only complex zeros, hopefully that means it's something that you recognize, and that, or you can make an XY chart to do that. So definitely it's a quadratic, and even if you didn't remember that it was plus 9, you should be able, or that it was up 9, you could make an XY chart, and if you plug in 0, you get 9. If you plug in 1 or negative 1, you get 10. And that's definitely not going to have any x-intercepts. So that's kind of a little vocabulary thing I just wanted to make sure we talked about. So making sure we answered this question, write it in standard form, that's this. Identify the zeros, that's this. And we said there are no x-intercepts. If it's a real number, the zeros and the x-intercepts are the same thing, okay? Okay, so I put Descartes' rule of sign on here next. I don't know if Mr. Allspaw gave you this in Algebra 2. I always taught this in Algebra 2 as a way to help, like, finding your PRZs. Because if you knew how many possible positive and negative real zeros there were, that it would help you like hone in on those PRZs. But the thing is, they're just possibilities, and so it's kind of up to you on how much you use Descartes' rule of signs. So it looks like Descartes, but you say Descartes. There's a lovely thing up here. This is my like math pun thing that says don't put Descartes in front of the horse, but I don't even know if you know that phrase, don't put the cart in front of the horse, but it says don't put Descartes, and it makes me laugh a lot. I don't know where it is. Oh, right here. Don't put Descartes before the horse. Like, don't get ahead of yourself. Like, that's what the phrase means, only they changed it to the guy, Descartes. It's a funny math joke. But it says, Descartes did a whole lot of math stuff, but this is actually named just for him. It's called his rule of signs. And it says, if you have a polynomial of degree n, the number of positive real zeros is equal to the number of variations in sign of f of x, or less than that by some even number. Aren't you glad I didn't make you write the whole thing? So here's a really easy test if you remember, if you did this in Algebra 2. At some point you would have stuff like 4 or 2 or 0 positive real zeros. 5 or 3 or 1 negative real zeros. No memories of this. The number of negative real zeros is equal to the number in variations of sign of f of negative x, or less than that by some even number. So I'm going to use Descartes' rule of signs as I do the next problem to kind of show you what it's used for, and then you can decide whether or not it's worth that extra step when you're solving those equations. Like those two equations on the chapter 2 test, where I said find all the rational zeros, find all the real zeros, Descartes' rule of signs is just one extra step to try to help you from having to guess like all of those numbers or try all of those numbers. Because if you find out there are no positive zeros, you can eliminate all those positive PRZs that exist. Okay? All right, so let's see if we can make some sense of this. So I want to make it clear on the directions on this. It says, state how many complex and how many real zeros the function has. Descartes' rule of signs can give us a list, a possibility, but you actually have to find some zeros to know exactly how many they are. All right, but let's use Descartes' rule of signs just so I can show you. So for possible positive real zeros, all you do is you look at the signs of the number. So for me, I just always go through and write the signs. Positive, negative, positive, positive. Okay, was anyone getting that? Positive, negative, positive, positive. And I'm just going to count how many times did it change from positive to negative or negative to positive. So positive to negative, that changed once. Yes? Negative to positive, it changed again. And then it stayed positive. So it changed 2 times. So that means for possible positive real zeros, possible, we should make sure to say that. It changed 2 times. Or the tricky part about the rule is or less than that by an even number. So that means you have to keep subtracting 2 until you can't subtract anymore or it would be negative. So 2 minus 2 is 0. So that means there are either 2 positive real zeros or there are 0 positive real zeros. Just any memory of doing this? You can get all this, Ross. For negative real zeros, you plug in a negative. Here's what's really great. All you're looking at is the exponent. If I plug a negative into an even exponent, is the sign going to change? Nope, it's an even exponent. But if I plug a negative into an odd exponent, like x to the third, do you agree that if it's negative now, that's going to be negative x to the third? So I always remember odd exponents are going to change signs, even exponents are going to stay the same. So 3x squared, if I plug the negative in there, nothing's going to change, so it's going to stay negative. What about x? Is it going to stay positive or is it going to change? Yeah, because that's a 1. If you plug a negative into an odd exponent, it's going to change to negative. The constant can't change. It's a constant. So that would say 1. How many times did that change signs? Like looking at this now. It's negative, 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 positive. 1 time. It only changed once, which means there is 1 negative real zero. I can't go down by an even number because 1 minus 2 is negative 1. There can't be a negative number of zeros. So there is 1 negative real zero. Okay? Do you have to do this problem? You don't, but it just kind of lets you check your answer to see if it makes sense. Like when you're done, you should have 1 negative real zero, 2 or 0 positive real zeros, and then depending on how many positive you have, it lets you know how many imaginary you should have. If you have 2 positive and 1 negative, are there going to be any imaginary zeros on this one? No, because it's degree 3, and 2 plus 1 already adds up to 3. But if there are no positive and 1 negative, how many imaginary zeros are you going to have? 2. So it's kind of a way to check your answers, and it kind of helps you sometimes. This would be really great. I should have given you this one on the test, right? What are my PRZs for this problem? Factors of the constant over factors of the leading coefficient. Oh my gosh. Plus or minus 1. So here's where Descartes' rule of signs, I think, can sometimes confuse you. A real zero could be more than just a rational zero. So what happens sometimes is people say, well, there's 1 negative real zero, so negative 1 for sure has to work, and it might work here. But just know, like, that negative real zero could be like negative 4 minus the square root of 3, right? That's a negative real zero. So just be aware of that. I think positive one's going to work. Is that true? If I plug 1 in here, I get, oh, it's not going to work. It's going to be negative 1, isn't it? 1 minus 3. Oh, no, that works, right? Plus 1 plus 1. Yes? Does this problem actually say we have to find what the zeros are? So here's where Descartes' signs can help you. If I know there is one positive 0 at x equals 1, does there have to be another positive 0? Because it's 2 or 0. You see what I'm saying? So there has to be 2 or 0 positive, which means we could just stop here. I'll keep working out to show you. But like I can say, since there's 1, I know there has to be 2, and I know there has to be 1. So we could say right now that there are 3 real zeros to this without actually working it all the way out. So that's where Descartes' rule of signs can save you some work. Let's say you didn't know that. You didn't realize it. Then you have to do just what you did on the last test. You have to divide this out and look what's left. So if I divided this out, negative 3, 1, and 1, I'm left with x squared minus 2x minus 1. And you just have to solve that. It's definitely not factorable, so really what you're just looking for, is it a real number or is it an imaginary number, to know how to classify it. Or if it actually says solve it, right? I think the next one says actually find the zeros. Then you would actually find it. This is one that I would probably choose to complete the square on if I was going to solve it, because it works out really nice. That I can take half of 2 is negative 1 squared and get 1. Add 1 over there. You got to remember, going from quadratic form back to solving, that you're doing the same thing to both sides. Or you can just do the quadratic formula here. I promise it works. Square root, square root. So we get x minus 1 equals plus or minus the square root of 2. 1 plus or minus the square root of 2. And x equals 1. That means there are 3 real zeros would be the answer to that question. State how many complex and how many real zeros. There are 3 real zeros. But I just like to show you Descartes' rule of signs to show you that if you're thinking through the problem, you don't necessarily have to solve it all the way out. And so that's why I like Descartes' rule of signs, because it saves me some work sometimes. And notice, there is 2 positive, because 1 plus square root of 2 is positive, 1 minus square root of 2 is negative, so it's a way that you can check your answers. Okay, let's look at this last one. Find all the zeros, right? So we're not just saying find all the real zeros now. We're saying even if it's imaginary, I want you to find it. And write a linear factorization, which means when you're done, you're not just going to say x equals 2, x equals 3. You're going to write them out as like x minus 2, x minus 3. That's what linear factorization means. This is a 4th degree, which means you're going to have to either find 2 PRZs, or you're going to have to hope that you can do factor by grouping after finding 1. Again, really nice that we're not checking any fractions here. That's factors of 1. So PRZs, factors of 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. I'm going to do Descartes' rule of signs again, just to kind of show you. Again, it's up to you if you want to do Descartes' rule of signs. But this is what I do exactly on my paper when I'm doing it. I just underneath here say positive, 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 negative, negative. Taking the signs. I can see it only changes once, which I know that means there should be 1 positive real zero when I'm done here. So one of my answers better be a positive real number. It might be a square root, but it better be positive. Or negative. Everything that has an even exponent stays the same sign. Everything that's odd is going to change. So 4th is going to stay the same, but the 3rd power is going to to change. X squared is going to stay the same. X is going to change, and the constant stays the same. So looking through there, it changes from positive to negative, negative back to positive, and positive to negative. So it changes 3 times. Go down by 2 until you can't anymore. So that means there's 3 or 1 negative real zeros. Again, that helps me. What if I got that there could be like 2 or 0 positive, 2 or 0 negative? That means that if there's 0 positive and 0 negative, like they could all be imaginary. And that means that I should be able to factor it or do something to find those zeros because PRZs aren't going to work. But again, kind of thinking ahead. Degree 4, if there's 1 positive and 3 negative, that means there would be no imaginary. Or if there's just 1 and 1, there would be 2 imaginary when you're done. So kind of thinking about that as you go. All right, I'm just going to check. And this is the part that just takes some time to do sometimes. Nope. Yep, I mean, I was doing -5 and -6 in my head, right? 7 minus 7 is 0. Oh my gosh, it's so great when 1 works. So, just like we did before, I'm going to divide out my 1. Get that. One plus 1 is not 1. 1 plus 1 is 2. What's really great is you know it should equal 0, so if you do something idiotic like me and say 1 plus 1 equals 1, that you can go back and find that mistake. So look what happens on this. We started with x to the 4th, and now we have x to the 3rd plus 2x squared plus 7x plus 6. We talked about that a lot of times when you're left with the cubic, you can do factor by grouping, and it saves you from having to guess again. But this does not work by factor by grouping. That does not mean that there's not any more zeros. It just means you have to keep checking. All right? So be aware of that now that we have x to the 3rd, we need to keep checking more numbers. Really tricky is I always skip the one I checked already, right? And I can see right now that 1's not going to work again. But, because they're all positive. But if there was a double root, just know that like 1 could work again if it was a double root, and that always tricks me because I check all the other ones first, and then I realize that it was 1 again, and so just be aware that sometimes that happens. I think this has to be a negative number now, right? We found that 1 worked, so that was our 1 positive real 0. So now the rest of them are negative, so now don't check any more positives. Check your negative numbers. Anybody find 1 work yet? No? I'm just going to go then. If I take -1, I would get -1 plus 2 minus 7 plus 6. Oh my gosh, it's my favorite problem ever. -1 works. Best problem ever when -1 and -1 work in problem. So what am I going to do? I'm going to divide it out again. And I'm left with x squared plus x plus 6. Is that factorable? Multiplies give me 6, but adds give me 1. 3 and 2 would need to subtract to give you 6, right? I mean, subtract to give you 1. You agree with me on that? Like, I don't think that's factorable. You want to say 3 and 2, but because that's a plus 6, like those have to be the same sign, so that's not going to give you 1 in the middle. So let's do the quadratic formula. So -1 plus or minus the square root. Look, you thought only 4 examples. This is going to be short notes, right? Who knew this was going to last forever? You need to extend page on the bottom of your. Yeah, you just would take half of 1, so you take a half and square it. So you do 1/4 to both sides. So that would be 1 squared minus 4 times 1 times 6 all over 2 times 1. So this is what separates from our last test to now. The last test, imaginary numbers, we didn't want to deal with those. We didn't talk about those yet. But now, even though that's going to be an imaginary number, I still want the 0. So if I take 1 minus 24, that's just negative 23. So I'm going to go ahead and pull the imaginary out and leave that as the square root of 23 all divided by 2. Which again is the same answer if you prefer to write it as -1/2 plus or minus I radical 23 over 2. I don't know which way you prefer it, but it's the same thing. Questions on where I got that? It's a lot of work. So we have 2 imaginary, and we also found -1 and +1 to work. Yes? 4 zeros. 2 imaginary, 1 positive, 1 negative. If it just said find the zeros, then we would be done with this problem. But it says write a linear factorization, which means they want you to write it out as a product of its factors. So I know you probably have no room left on your paper. But the linear factorization, really easy with 1 and -1, right? That's just going to be x plus 1 times x minus 1. Just like the first problem we did. For these imaginary ones, I just change the signs as I go. So, I don't know. What do you want to do? You want to use the big fraction or the 2 fractions? Big fraction. If, just like with -1, I changed it to +1. So this is a -1, so I'm going to say that's x plus 1. And there's 2 of them here, so you have to write it twice, all right? So I'm changing the sign. So the top plus is now going to be minus I radical 23 over 2. And the next one, this is still a -1 out front, so that still changes to +1. But this minus would now be plus I radical 23 over 2. Told you it got ugly. I want to advise you that when you look at the back of the book, their answers look a little nicer, and I'll show you how to do it, but I just want you to know I'm okay if you write your answers like that. Those are the zeros, and if you want to write them like that, you can. But they simplify it a little bit more, and they say, well, that's kind of ugly to have the 2 in front of that. So they just multiply through by a 2. So they say that's the same as 2x plus 1 minus I radical 23. So then you could move that over and then divide by 2. I don't care which way you do it. I just want you to know when you look in the back of the book, you'll be like, why is there a 2 in front? Why isn't there a fraction? And so theirs look a little nicer, like this. And then they have their other stuff. But I don't care which way you do it, as long as you can do it. Really not that much different than what we just took a test over, except for imaginaries and linear factorization are the 2 separate things that we've added today. So this is homework 2, 5, day 1. A lot of it kind of goes through just like our notes did today, of saying write it in standard form, give the x-intercepts, write the polynomial given the zeros. 17 through 20 are matching a graph given the zeros and multiplicity, so that kind of goes back to what we did on 2-4. Use in behavior and multiplicity to help you match those up, and we can talk about them tomorrow. And then 21 is just state how many complex and real. And then 27 and 30 are like our last one. 27 isn't as bad, it's only a third degree, but 30 is like the one that we just did, the fourth degree one. So there's really only two that you have to do a lot of work on. The rest of them are not as bad to do, but work on those. We'll talk about questions tomorrow, and then we'll finish this section talking about what if I gave you a zero, how could an imaginary zero, how could you find the rest of the zeros, and some stuff like that. So. Don't forget about test corrections, especially since it's fall break